for you to meet Joe Nagan. He's an energy expert who worked here on the Wisconsin Trend home. And Joe, can you tell us, as an overview, how this home compares to a traditionally built home?
Sure. What we do, Megan, on every home is we do a real thorough computer evaluation up front of the homeowner's plans and dreams. We don't ever want to change the building, but we evaluate each component of the building that adds to the operating cost, look at cost-effective conventional practices if we can to improve that. For instance, starting in the basement on the slab floor, we would normally see no insulation under the slab floor on a well-built code home. Here we have R10. The foundation walls were bumped up to R23 compared to usually R5. The above grade walls were bumped up to a total R value at 33 using standard stick frame construction but with advanced framing, and compared to R19. The windows were bumped up to triple pane at a U value of 0.19 compared to an average of 0.35, and the attic was insulated to an R60 compared to 38 or 49.
Now, how do those choices translate into energy savings?
Well, again, since we did elaborate modeling up front, this home built to a well-built code home in Wisconsin would have a total operating cost estimate for heating, cooling, water heating, lights and appliances, and service charges of about $3,000 per year, an average about $350 a month. This home estimated to be at least 50% of that, around $1,558, for about a $150 per month operating cost.
Wow, I want to see why that is. Let's start in the mechanical room. You talked about the mechanics of the home. Can you describe what's going on down here?
Oh, sure. Megan, in addition to the high-efficiency ground source heat pump that we have doing our heating, cooling, and partial hot water servicing, we have the heat recovery ventilator providing our ventilation for good indoor air quality and moisture control. What's often left out in the design of a new home is people know that they should build the home draft-free, which means tight on the construction, but very seldom do they ever spend enough time dealing with, okay, how do I ventilate that building now to control my indoor air quality, control my operating cost of that ventilation air, how do I control moisture in the wintertime? In this home, we selected a heat recovery ventilator, and we'll take the cover off to show you what it looks like so we can explain how these units work. You're often going to find that people just throw them all in a category of air exchangers. So we don't have a problem with that because that's what this is. The core of the unit, or the guts of the unit, if you will, is a core, a laminated core, protected both on the stale air from the home and the fresh air from the outside to prevent the core from getting plugged up, because once these plates are dirty, they lose their recovery efficiency. But the general workings of the unit is pretty simple. There are no heating and cooling equipment. There's no light bulbs for heating. It's simply the function of heat exchange based on conduction. All heat recovery ventilators look identical in construction. They're made up of many laminated plates. So if we took all these plates and laid them on the floor, we might have a couple of hundred square feet of surface area. And to recover or reject energy, it's a function of how much surface area do we have. So rather than have a 200 square foot unit hanging here, they just laminate plates together. But there's a direct airspace between each plate. And in the actual function, on one side of the plates is the stale house air we're trying to reject, and coming in the opposite direction, but on the opposite side of each plate is our outside, hopefully fresher air. And how that works is by a simple process of remembering that in a building, everything goes from warm to cold. So what happens is on these plates, they're able to actually recover about 70 to 80% of that sensible heat that we already paid that equipment to put in the building. So now if we got air coming in at 0, we can pre-temper that incoming air before we put it into the home to about 40 to 50 degrees Fahrenheit, which reduces the load on the heating equipment.
How much energy does this save? In a typical home, how much would this save?
In this particular home, since we did so many computer simulations, running this same unit compared to running an exhaust-only system where we're simply throwing the air out, it modeled between $100 and $105 a year of annual savings. And again, that's still $105. I mean, if people really want to deal with operating costs and the associated environmental impact of the electrical generation by a power plant, you really need to look at all those loads.
Well, and that all adds up to paying off the cost. And what is the cost for a system like this?
On a typical new home, as a ballpark figure, we'd see anywhere between $1,000 and $2,000.
That's really exciting. All right, what else are we going to see down here?
Well, I thought as long as we were downstairs, we should take a look at some of the other equipment right in line of sight here. In this technology developed in Canada, when that water is coming down from a shower at 90 to 95 degrees, going right through the floor drain, water coming down a pipe actually sticks to the inside of the pipe. It doesn't fall in the middle. It sticks to the surface of the pipe by adhesion. So if we have that energy touching this copper, highly conductive material, the concept is every time there's a gallon of hot water taken out of the water heater, immediately there has to be a gallon brought in as cold water. So that 55-degree water coming in, roughly at our temperature here, we can heat that incoming water to about 85 to 90 degrees. It's all about temperature differential. So now instead of 55-degree water going into the water heater that's got to be picked up to 120, I'm dumping 90-degree water in there. Now that only has to be brought up to 120. So in the bigger green concept, we're not only saving water, we're saving on the emissions as well.
So simple, so effective.
That's correct.
Come tell me about what's over here.
Sure. Megan, what we have here is another both water-saving technology and energy savings technology called an on-demand pumping system. Its primary intent is to help consumers deal with waiting forever for hot water at a fixture. The concept is pretty simple, unlike what's currently being done in homes. When we have the on-demand pump, it allows the consumers, before they open the fixture, to tap a momentary closure switch, which activates the pump. So there's a little lifestyle adjustment, but the pump only comes on long enough to move water throughout that circular distribution loop, and then it immediately shuts off.
Terrific. Thank you. You've given us such a great education today.
Well, it's my pleasure.
Saving energy and keeping our homes comfortable. Isn't that what it's all about? If you'd like more information, visit our website at powerhousetv.com.